Hello, Paul. I thought I'd show you how to derive Newton's equations for constant acceleration. The equations that you taught me in college, and now I've got to the stage where I can actually derive them um, using integration and methods like that. So it's quite a big stepping stone, or has been since this all started for me. So right, here we go. So um, you remember that x is a position, something. Uh, and if you take the derivative of the position with respect to time, that is equal to the velocity. And if you take the second derivative with respect to time, it becomes the acceleration. Okay, so what if your acceleration is constant? So right up here, the acceleration being a constant, we call it a sub-zero. It doesn't really matter about the sub-zero, but we'll call it that anyway. So if we want to get from this bit, second derivative with respect to time or position, you take the integral, of these, and then you get the velocity, which is this bit. So what we're going to do is take the integral, sorry, take the integral acceleration, which is equal to the velocity, take the integral of this, but this is respect to time, dt, respect to time. So what we end up with is v is equal to a t, because this is a t is equal to t to the power of 0. Anything to the power of 0 is equal to 1. So you could just write that things to substitute. So when you take the integral, this changes to a 1, so 80, and then plus the arbitrary constant, which you have to implement when you take a integral. Because when you're in an equation like this, there's actually a field of numbers. This is a linear equation because there's no squares or nothing, so this is just a straight line. But when you put a plus c in there, then it pinpoints that onto an exact line. Like there's a number of line or infinite number of lines, pinpoints it onto an exact line. So what we're left with is 80 plus c. Well, at v is equal t is equal to 0, this becomes a 0 plus c. So the initial velocity v0 must be equal to c. So we call it v sub naught 0 because it's the initial velocity. So we can rewrite this whole equation as a velocity is equal to acceleration times time plus v naught. And you might see this in books normally nowadays as v is equal to u plus at, where u is equal to v naught. Your initial position is u. Okay, the next step, right, into the corner. Right, the velocity is the derivative of position with respect to time. So what we need to do is we need to take the integral of these, and then we equal equals x. So we're going to do that. Take the velocity is equal to, I know we won't write it like that. We'll write it like we initially did. At plus vu v naught. To take the derivative of these with respect to time, And what we end up with is the position is equal to at squared divided by 2, because what we're doing is this is 1, so we're raising this by, I mean, we're adding 1 onto it, it becomes 2. 1 plus 1 equals 2, and divided by the new number. So, and on this part, we've got the integral of v naught, which is plus v naught t, because there's a t naught here, but we're adding 1, and then plus c, our arbitrary constant, and we're taking an integral. Well, this is another function, x of t. So when x of t is naught, this becomes naught, this becomes naught, and you end up with the initial position, xi, get rid of this, is equal to c, new c. So we can rewrite this whole thing as x is equal to, oh, x is equal to 1/2 at squared plus v naught t plus, and this could be seen in books nowadays as x, or no, it's put as s. The displacement s, displacement s is equal to, how do they normally write it? Xi, so that'd be initial position, so plus v ut plus 1/2 at squared. And these are constant acceleration equations of motion from Isaac motherfucking Newton by himself. Cool, man.